You might have to watch it.
So I was very deliberate with my examples because I don't want this to go like out of order. So I've numbered them and everything like sequentially. So I'll try to draw some triangles here. You have to draw them as well. If they're not perfect, then so be it. I am going to cheat a little bit and use my straight line tool. So in that sense, I have a, what's that? I don't know what you want to call this. Let me draw this triangle and then I'll come up with some kind of great idea for us to title these notes. So yeah, that looks pretty good. So let's go ahead and give it a title. I don't know if Brooklyn's watching these videos at home, but if she is, then she'll want to know what we're doing. So it's the 27th. Oops, I don't know why I put a colon in the date. What a rookie. Oh, no. Oh, it's back. Oof. God, I thought I just had to do the whole thing again. Let me try again. The slash big guy. There you go. Let's talk special right triangles. And this is the like the prologue, if you will, to allowing us to get into the unit circle. And the unit circle is the prologue that then allows us to get into other aspects of trigonometry. So one thing leads to another. So you all had to take geometry, and I saw a lot of nodding heads, like you totally knew what I was talking about when it came to, whoa, when it came to these particular types of triangles. So this one you can probably tell from the scaling and the way I drew it, but let's just make it official. This is a what we call a 45, 45, 90 triangle. It's also called a right isosceles triangle, but in its trigonometric sort of application, we more call it a 45, 45, 90. And a relationship that you, again, I'm going to see what you know kind of as we go here. If the length of this side is 5, can you give me the other two lengths of the triangle? What's that? A typical answer, like if I address this with, say, an 8th grade class, is they ought to say no. Like we can't, because in order to use the Pythagorean theorem, you need to know two sides, right? But there's a caveat here. Yes. Five for the other side and root two. Well, 5 root 2. Good memory. Very good. So hopefully this comes flooding back to you. Because this particular triangle is isosceles, it has to be, with the 245s being the same. Then that means that this side over here is also 5. And then Brady's clearly got his memory working full tilt here. And you guys will remember that in a 45, 45, 90 triangle, the hypotenuse is whatever the length of the leg is times the square root of 2. So we would say in this case that the hypotenuse is 5 root 2. Seeing that for the 20th time, is that okay to assume? Remember this a little? Okay. We also have another type of special right triangle, and it is the 30, 60, 90. So again, I'm going to cheat a little bit and use my straight line. You get to try to freehand them unless you have like a ruler on your desk or something. But this triangle is more, I don't know that my scaling was knock it out of the park good, but it's definitely not isosceles this time. So angle-wise, we're again working with a right angle, of course. And then we have a 60-degree fatter angle and a 30-degree smaller angle. And again, we call it logically a 30, 60, 90. So there's 45, 45, 90, and 30, 60, 90. And with 30, 60, 90, again, the test here is if I give you one side, if I said, for example, that this little leg down here is 4, could you tell me the other two? And the normal pre-geometry class response, again, is no. A really good student would say, no, I need two sides so I can a squared plus b squared equals c squared. But you clearly remember this one too. What are the other two sides?
Isn't the other leg 4 root 3?
It is.
And then it's 2 times 4.
Impressive memory. Good. So these are going to be really the fundamental relationships that are going to get us through the next 10, 15, 20 minutes is if I own this, like, then I should be able to work in any direction from any side to the other two sides. So let's generalize this so that and I'm going to just take the lazy route here. I'm going to erase some things. To generalize, based on what Brady helped us recall there, we can then say that if you have a 45, 45, 90, if you have a leg of x, then the other leg is also x, and the hypotenuse is x root 2. And if you have a 30, 60, 90, and you know that the shorter leg, this is important that it be the shorter leg, is x, then the longer leg is x root 3, and the hypotenuse is 2x. Good, good. So having said that, before we go to the next ones, let's talk about working backwards. What if I gave you a 45, 45, 90, and I gave you the hypotenuse? How would you work backwards? Let me put one up here, and I'm just gonna be lazy and recycle my same pictures because I think they look really good, and I don't want a chance making new ones that look bad. So let's say I had a 45, 45, 90, and I told you that the length of the hypotenuse was 6. Good job. We divide by the root of 2. I mean, logically, if you multiply by the root of 2 to go from leg to hypotenuse, then you divide to go backwards. And so the length of this side down here is 6 divided by the square root of 2, which you probably know from some previous experience with either myself or Mr. Manlove or both. We're not allowed to leave it like that. Do you guys remember how to fix it when there's a root in the bottom? What'd you say? We multiply the top and the bottom both by the root of 2. In math, we always want to rationalize our denominators. We never ever want to leave irrational rooty-tooty numbers in the bottoms. So we fix it by killing it off by multiplying it by itself. And then we wind up with the square roots of 2 on the bottom. I want to say they cancel out, but they just become 2. And then on top, we get 6 roots of 2. And then if we reduce that, what do we get? We get 3 root 2. It's a little bit, I think, less useful to try to do this one formulaically. Like I could call the hypotenuse x, and then I could call the shorter leg like x over 2 root 2. There just comes a point where you saturate your paper with enough crap that it loses value. So I think as long as we remember the x root 2 relationship, then we can work backwards by just doing simple division like this. If that side is 3 root 2, then of course this side is also 3 root 2. And we can work the same way. We can do a 30, 60, 90 triangle in the same way. Who says that we have to start with the short leg? We can start with something. We'll keep this one pretty simple. And then this one, really theoretically, we should do 2 different ones. So let's say that the hypotenuse here is 12. You should be able to logically, in a very specific order, work your way around this triangle. What's the bottom side?
6.
Yeah, we know that relationship is double half. And if he's 6, then what's the long leg?
6.
Good. Now, obviously, I think the problem is more difficult if instead of starting with the hypotenuse, if we start with the longer leg. So let's say that the longer leg is 10. It's going to be a little messy, but we're not scared. So what's the relationship when you go from long leg to baby leg?
Yeah.
Good job. So we're going to have to divide by root 3. So if I want to find the bottom side, this one down here that I'm kind of circling, then I'm going to have to do some math. I'm going to have to take the leg that I know, 10, and I'm going to divide it by the root of 3. Makes sense. When going the other way is times, well, flip-flop it. And again, we can't leave it like this. If we multiply the top and the bottom both by the root of 3, we wind up acceptably saying that the answer is then 10 root 3 over 3. So that becomes the length of the short leg. And again, could you make a rule for that? Sure. If you wanted to. Say if the long leg is x, then the short leg is x over 3 root 3. I just don't know that it's worth the effort. If that short leg is 10 root 3 over 3, then what's the hypotenuse? Just multiply it by 2. So it's 20 root 3 over 3. The point of this last 10 minutes is to show us that we can do anything with a special right triangle. If you give any one of us any one side, we have the skill set to be able to find any of the other 2 sides. provided that we're working within the confines of these two special types of triangles. So having said that, now I'm going to do two very specific problems. And the numbers that you're going to see in these two very specific problems are the numbers that you're going to be hearing and saying a lot in the next weeks or however long. So again, I'm going to recycle, and I'm very, very purposely going to put each triangle, if you want to get ahead of me, draw these triangles and give the hypotenuse a value of 1, exactly 1. So we're going to backtrack and work out the lengths of these sides. And then I think we'll definitely get to the unit circle today. And hopefully I'll be able to show you why the number 1 is so important. So if I have a hypotenuse of 1 and I want to work backwards, how can I find the lengths of these legs? Same, you know, second verse, same as the first or whatever. Like, it's the same. I'm going to take the one that I know and I'm going to divide by the root of 2 since I'm in a 45, 45, 90. So this would be 1 divided by the square root of 2. What does that simplify to become? Yeah, you better get used to hearing the sound of that coming out of your mouth. Root 2 over 2 is going to be a real hot answer in coming days. And if that horizontal leg is root 2 over 2, then the vertical leg is also root 2 over 2. Commit that triangle to memory. Make sure it's in your notes. Make sure it looks good because it's a big one. Okay, now we're going to do the same for the 30, 60, 90. And I'm actually going to tilt my 30, 60, 90 just so that it matches the unit circle. So part of my preparation was not anticipating being lazy. So I'm going to redraw this triangle laying down like it should be. And that doesn't matter. It's just, again, it'll make more sense when you see it on the unit circle if it looks the way that it will in the circle. So I'm going to reorient like this. Sorry to make you do that. That's my bad. Give you a chance here to get fixed up. And again, we want the hypotenuse to very specifically be 1, because that'll turn out to be the radius of a circle whose radius is 1. The hypotenuse is 1. Then what is the vertical, the short leg? 1/2. And if the short leg is 1/2, then what's the long leg? 1/2 root 3, which we from this point on are going to call root 3 over 2. So I'm going to hand out the unit circles and we're going to start looking at it and talking about some angles and some values. And you just never know, since I haven't taught trig in like a decade. Like, how long will this take? I don't know. But I'm going to pause it and then I'm going to hand them out and then we're going to talk about starting to fill some stuff in. And hopefully if that went, it's really going to suck if you look at the circle and you walk out of here today and you still like have no idea why we did that just now, because those triangles are the triangles that make up the unit circle. So I'm going to pause this and I'll get these handed out. Recording for Brooklyn. So if we were going to do, I know, right? If we were going to do a circle and find its circumference, do you guys remember the formula for the circumference of a circle? R2 times pi. It's right. It's real dirty how you said that, but it's functionally it's correct. Yes. We say 2 pi r is generally kind of a cleaner version of that. R2 pi is pretty amazing. I don't think I've ever heard that before. Same diff, same. Some people say pi times diameter, and that's fine too. But 2 pi r is a pretty common way to say the circumference. And remember that the circumference of a circle is the distance around it. So if you pick a point on the circle and travel all the way around and return, that curvy distance is called the circumference, and that is the formula for that. So if I'm working in a circle whose radius is 1, which we are, what is the circumference of our unit circle? Good. So the circumference of the unit circle is 2 pi. That's important. This can get really painful for the brain because what we're about to do is switch our thinking from angular measure to radian measure. So in a minute here, we're going to switch, and instead of seeing an angle coming up like this as a 30-degree rotation, we're going to see it as a radian measure, which is a fractional part of a full 2 pi rotation. Took me a lot of time as a kid to get my head around how that works. And so if I go back to my unit circle, which is here, we would agree that at the beginning, in terms of what we call radian measure, I have gone nowhere, so I am at 0 radians. Now, what's going to help this make sense to you, I think, is if we don't go baby steps. What we want to do is chunk out what I hope are the obvious ones. And I think the first obvious one is this. If I went all the way around the unit circle and returned to my home base, how far have I traveled? What's the circumference of this circle with a radius of 1? So I have traveled 2 pi radians if I make the full journey. Now, having said that, if I go halfway across from the far east side over to the far west side, how many radians have I traveled?
1.
1 pi, which we just call pi. Now, let's subdivide this yet again. If I go to the top, we know that to go from the beginning to the far right, or excuse me, I'm back far left is pi. How far in radians is it to go from the beginning to the top of the circle?
Pi over 2.
Nice job, guys. Pi over 2. And let's finish with the other quadrantal angle. Quadrantal angles are the easiest kind of points of reference because, you know, we know they're 0, 90, 180, whatever. And same for radians. Like they're the easiest ones to first memorize because they logically are just half pieces of pi. So if I go all the way to the bottom of the circle, how many radians is that?
3 pi over 2.
Impressive. Very good. And that can be explained many ways. I think the simplest way to think of the bottom of the circle is to think about how many quarter turns did it take to get there. So you had to go 1 pi over 2, 2 pi over 2, 3 pi over 2, right? And that gets you right before you get back to 4 pi's over 2, which is, of course, 2 pi. So the bottom of our unit circle, we should have our radian line measured at 3 pi over 2. The next logical place to go is to talk about now the halfway quadrantal angles. And those are the 45-degree splits. So let's kind of see how our math goes here. Sorry, I gotta figure this out. Let's see. Yeah, I gotta redo this. Before tomorrow, I'm gonna get it like into my other software so I can. This is driving me crazy. So let's start with this red point right here. What would you say that one is? To make your life easier here, I would tell you to think of it relative to this purple point. Like that should break you free. If you know what the purple point is, which is pi, right? If it takes pi to get all the way across, how many little red journeys would it take to get to the purple? Right. I hope you agree that if you go 4 of these journeys, so if I go from here to here, that's 1, here to here is another, here to here is another, and then here to here. So it takes 4 equivalent sized journeys to get to pi. So what is the red dot? What's his radian measure? Good job, pi over 4. So your second line in quadrant 1, don't go to the first or the third lines yet. Those are the weird ones. Our second line in quadrant 1 should be pi over 4 radians. All right, let's head to the midway point of quadrant 2 over here. I know it's kind of small, but that red dot. Again, I would encourage you to think about what I just drew with those red arrows. How many equivalent journeys of pi over 4 does it take to get to that red dot? 3. So we name it as 3 pi over 4. And in keeping with this theme, let's obviously skip the purple dot because that's 4 pi over 4, which we already have as pi. Let's head down to the midway point of quadrant number 3. And in quadrant 3, again, I implore you, just use common sense. Think about how many quarter turns does it take to get to that red point? 5, right? You agree. If you did 45 degrees or pi over 4, 5 times, you would be pointed perfectly to the southwest. So this one is 5 pi over 4. So far, so good. Okay. And then finally, let's head over to quadrant 4 and talk again about the midpoint. Good job, Ellie. It takes exactly 7 of those 45 or pi over 4 turns to get there before we return home to 8 pi over 4. So this last stop down here is 7 pi over 4. You should now have every blank filled in except for the artists formerly known as 30, 60, 120, 150, so on and so forth, right? So filling those in now, I'm going to, again, just, you're all smart people. So if we just talk in terms of like portion size, if I wanted to figure out this one, think again about how many of these, good, I hear that S word. Yes, how many of that journey right there does it take to get all the way over to here? And the answer is 6. And you can understand that multiple different ways. You can say, well, I mean, you could come at it from 5 different directions. At the end of the day, it's 30 degrees in its angular measure, and it takes 6 30s to make a 180. So because it takes 6 little journeys, what do we name that first blank as? So now we talk about the next one, which is exactly right, Ellie, is right up to here. And that takes 1 pi over 6, and it takes another pi over 6. Or you can think of it as 1/3 of the way to 180. Again, sky's the limit. Whatever math makes the most sense for you, it is definitely pi over 3. Okay. Now, as we go through the rest of this, quadrants 2, 3, and 4, again, we're working in chunks of pi over 6. That's really the key when you forget these, is to remember that we're either working, if we're at a mid-quadrantal angle, we're working at chunks of pi over 4. And if we're at one of the awkward early late angles, we're working with chunks of pi over 6 and pi over 3. So having said that, I'll circle one and you can tell me what you think it is. What is that? It's not pi over 2 because that was already taken up at the top. Say it again. I love that answer. I'm going to reduce it with you, but I can tell the way you chunk that out. So there's 2 ways the human brain will attack this. Josie's attacked it by seeing it as a collection of 4 small moves. Josie saw it as there's 1 pi over 6, there's another pi over 6, there's another pi over 6, and there's my 4th pi over 6. Good on you. Another way to say it, yes, if you didn't want to have to reduce the fraction, is you could view it as 2 larger journeys to get to the same point. You could say, I went to here. How long is that journey, the purple arrow? That's 1 pi over 3. And then if I take another 1 pi over 3 journey, I get to my destination, leaving me with the conclusion that this angle up here is 2 pi over 3. Oh, of course, yes. Yeah, we don't want there to be multiple possibilities. Like if you say 2 pi over 4, that's not okay, right? So everything gets reduced. That leads us to this next one. I'll circle him in green. I don't know if that shows up there. Oh, you can see that. What's his radian measure? We can't do him in terms of pi over threes because he's not a whole chunk of pi over 3. Good. So this one has to be subdivided into sixths. It takes 5 30-degree jumps to get to 150. Or 5 jumps of pi over 6 to get to this particular angle. So the measure of that particular angle is 5 pi over 6. Still so good? Everybody okay? All right, let's head down to quadrant 3. Once we enter quadrant 3, our first stop is this one that I'm circling in red right here. And what's his name? Good. The fact that you say that tells me you're really picking up what I'm putting down. I understand that it takes 6 pi's over 6 to get to the far right corner, and I just drop another pi over 6. That little 30-degree we come to know as pi over 6. So 6 pi's over 6 plus 1 pi over 6 equals, good job, you guys, 7 pi over 6. Our next stop can be built with pi's over 3.
4 pi.
And he is 4 pi's over 3. And that is this purple one down here that I am circling. He is 4 perfect movements of 60 degrees. If you move 60 degrees 4 times, you get to 240, and that's right what that angle is, 240. So he is 4 pi's over 3. Good. We're almost there. Finally, we head over to quadrant 4, and this will be the point where we can say we now have every blank for angles or radians filled in on our unit circle. We we will not talk sine and cosine today, but maybe tomorrow I'll start class by pointing at an angle and having you tell me what it is, just from memory, something like that. So as we head into quadrant 4, we already have 4 pi over 3. If we go one more full journey of pi over 3, what is this next point here? Nice. And this last one cannot be expressed in terms of pi over 3. You could think of it as coming at it from the long way, or you could think of it as this. How far would you have to back up from the starting point to get to this last angle here? 1/6. And so what's 12 pi over 6 minus 1 pi over 6? So our final angle in our unit circle is 11 pi over 6. At this point, every blank should